Then the next presentation is also going to be an online presentation. There are several online presentations coming up now. The next one is by Ole Andreas Alsos, also at NTNU, the same university as myself. He is Associate Professor and Vice Dean of Innovation, and he's going to talk about maritime autonomous surface ships, automation transparency for passengers and other vessels.
Hi, my name is Ole Andreas Alsos. I'm working at the Department of Design at the Norwegian University of Science and Technology. And this talk is about automation transparency for nearby vessels. This is the float man who transported people over the canal in Trondheim in the old days. On the canal, he could, with eye contact, nods, shout and winks, avoid deadlocks, dangerous situations and collisions. So he was transparent about his situation and future intention. And this made it easy for other ships and boats on the canal to understand him. And he was very attentive to other ships and could understand what maneuvers they were planning to do. And all in all, this supported safe travel on the canal. This is Milan 2, an urban autonomous passenger ferry developed in Trondheim that can replace the floatman. It can transport passengers over the canal without crew on board, and the operator is moved into a remote control room. However, to make the operator, the passengers and other ships in the area trust the ferry, it needs to communicate with them what it's thinking and what it's going to do. And autonomous ships come in many sizes and application areas, like Jarabirk and the Asko container carrier. For these kind of ships, the bridge will move into shore-based control center in the future. But first, some definitions. We are talking about explainable AI and automation transparency in this talk. And it's about making artificial intelligence understandable to people, to understand the inner workings of the algorithms. And this is foundational to ensure trust and efficient interaction with AI systems. However, AI made entirely transparent in its workings does not necessarily mean it's explainable. And lack of automation transparency can be a bottleneck for people's trust in autonomy. Our definition of automation transparency in the context of MASS is their ability to express its current state and future intention to nearby ships, but also the ability to perceive the current state and future intention of other ships in the area. In a previous paper, we defined stakeholders of MASS as developers who develop the algorithms, operators of the ships, passengers on board, non-SOLAS ships and SOLAS ships in the area. Non-SOLAS ships usually sail with a crew with varying seamanship training, experience and safety culture. It's usually smaller vessels below 50 feet and include sailboats, leisure crafts, smaller fishing vessels and kayaks. And these vessels often have a limited equipment for maritime communication and usually communicate with other ships through analog means such as distinct course changes, navigation lights, shouting, and, depending on the size and type, radio communication on VHF. SOLAS ships, on the other hand, have trained and experienced mariners with a strong safety culture. These can generally be regarded as merchant ships, such as vessels transporting cargo or carrying passengers for hire. The ships are usually well equipped with a range of different analog and electronic tools for maritime communication. However, there is a lack of research on how MASS may communicate efficiently with both these vessel types. And to help us analyze current methods for maritime communication through a MASS lens, we interviewed 5 subject matter experts. And in the interviews, we discussed several research questions. First, what forms of communication are applicable to today's SOLAS and non-SOLAS ships? How these express the ship's own state and intention and perceive other ships' state and intention. And finally, we discussed the gaps in the communications methods when transferred to the AI of MASS and how these gaps might be resolved. Communicating a ship's state and intention to other ships is usually done through various means of maritime communication. And in this figure, we show different means of how traditional ships communicate, both directly and indirectly, and show the different ranges of the communication means. What we see is that communication can be perceived or expressed, broadcasted to all the ships or directed to one ship. It can be analog or digital, or continuous or discrete all the time. What we see is that the different communication methods have different characteristics. We also see that maritime autonomous surface ships perceive the environment through a range of different sensors. We also see that non-SOLAS vessels and MASS can only communicate through a subset of these communication methods, while SOLAS vessels can use all of them. And we also see that non-SOLAS and MASS are not overlapping. That means they will have problems communicating to each other. We also see that adapting current maritime communication to MASS will have a different cost and different value. Some of them will be very expensive to develop, but will have a high value, such as radio. There is a need for additional ways or methods of communicating the autonomous ship's current state and future intention to nearby ships to ensure safety at sea. We propose a focus on automation transparency to alleviate these problems. We suggest 3 main strategies for increasing automation transparency, and these should be done in parallel. The first is develop the MASS sensors, algorithms and technology so that they can understand and communicate with ships within existing frames of maritime communication. One example is how MASS can express its intention to other ships through movement. Unstable movements, such as to the right, would not be trusted. The second strategy is to develop existing communication so that it's easier for MASS to use it, such as maritime messaging that are adapted to MASS, or revise AIS with new message classes so that MASS can communicate its state and intention through it. The third strategy is to develop fundamentally new ways of communicating with other ships that are better adapted to the way computers and artificial intelligence perceive and communicate with the world. Example is through physical design of the MASS, the superstructure, with no bridge. It's to display communicating messages and symbols in the axis, to communicate with light signals around the superstructure, to include past states in automation transparency, and to prepare MASS with sensors and actuators for future automation transparency and maritime communication. To give you one simple example is how to use light to communicate its current state and intention. And again, all these should be developed in parallel. To conclude, MASS have limited ability to perceive the state and intention of nearby ships. They have challenges communicating their own state and intention to nearby ships. And to improve automation transparency, we recommend to develop MASS sensors, algorithms, and technology so that they can understand and communicate with ships within existing frames of maritime communication. The second is to evolve existing communication so that it is easier for MASS to utilize it. And the third is to develop fundamentally new ways of communicating with other ships that are better adapted to the way automation and artificial intelligence perceive and communicate with the world. And these recommendations should be developed in parallel. Thank you very much.
Okay, thank you, Ole, for a very transparent presentation. Are there any questions? Was it so transparent? I have perhaps one question I could ask. You mentioned shouting, and then I saw that you placed that under not so high value. But it is explicitly stated in Colrex that you should have lookout by means of sight and hearing and other means. So do you have any further thoughts on that? What is the role of sound? Should autonomous ships be required to have microphones to listen? Should they use sound signals? Yeah.
Yes, I think so. I think that every autonomous ship should have all the sensors needed for all kinds of communication. However, to be able to understand, for the autonomous ship to understand shouting, it would require a lot of effort and would cost a lot. But yes, all the ships should have all the sensors, cameras, microphones, and so on to perceive the world. Not only lidars, radars, and infrared cameras, and so on.
I think Alan McGee has a question.
Hi, Ola. What role do you think the vessel traffic management system should have in sort of directing traffic the way that we have air traffic controls for shipping and for autonomous ships in particular?
Yeah, I think that it will have when the maritime autonomous surface ships are more common, we will have this not air traffic controls, but something similar for these ships that can guide them, and at the open sea we can see a future where one operator can monitor several ships at the same time, maybe a whole fleet of ships. But as they get closer to the shore, and when they get to the harbor, they will be controlled by fewer and fewer operators. And at docking, for instance, I would expect that maybe 2 operators or more take care of one ship. So it will work much in the same way as the air traffic control, I would expect.
But I guess there's a fundamental difference in that the current rules or practice is the shipmaster always has control of his ship. Even the port pilot is there only as advisor. But the captain is ultimately responsible for his vessel, so he has the final say. Whereas I think for aircraft on approach, it's actually a centralized control, so that's different.
Yeah, that's correct, and I think you're right in that the role of the air traffic controller and the ship controller will be slightly different. And that's why I think the surface ship, the autonomous surface ship, need to be equipped with a lot of sensors, not only for the autonomy algorithm, but also for operator awareness. That means that we have to have other kinds of sensors, like microphones on board, like cameras that give a good overview of the ship, both around and on board, to the remote operator. So we need, in addition to the autonomous sensors, we need a range of sensors for the operator to give them a good situation awareness. They should be able to take over the control and remotely control the ship from the shore. However, they could also be on board.
Thank you once again for the presentation.